I'm going to walk you through today's lab practical. There were over 30 versions I've accumulated over the years, but I'm going to show you using Epsilon. You probably didn't have that form, but even though the chemicals and substances may have been different for you, the tasks were the same for everybody. That's what I want to emphasize. All right, now for task 1, I am asked to determine the mass of the oxygen atoms in a specific amount of sucrose in beaker 11. So you could have massed that substance out first. I'm going to use the periodic table and get the percent composition first. So for carbon, using the formula, I can see that there are 12 carbons, and the mass for carbon from a periodic table is 12.01, and that's going to give us 144.12. Now for the hydrogen component, there's 22 hydrogen atoms in a molecule of sucrose, and each hydrogen has a mass of 1.008, 22.176, so 22.18, and I don't really need units in terms of AMUs or grams, because this is an intensive property. The percent composition is going to be the same whether I'm determining that percent composition for a single molecule or however many grams is in the beaker. It's going to be the same percent composition. And finally, oxygen. From the formula, I can see there's 11 of them in the molecule, and the mass for oxygen 16.00. $176. So now I'm going to add these up. And this is my molar mass for sucrose, or my molecular weight for sucrose, 342. I'm going to go to 1 decimal because I know there was precision there for sig figs for the oxygen. All right, so now I am asked specifically for the oxygen atom, so I'm going to get that percentage by, it's already set up here, so I'm going to put that in my calculator. Multiply by 100 to get me a percent, and that's going to go as 51.4% of sucrose is the oxygen. So now that I have that percent composition, which is an intensive property, I can apply to whatever quantity I want to. So here's beaker 11 with the sucrose that we're looking for. Let's turn our scale on. Let it calibrate. Get a clean, dry beaker. This one looks clean and dry. Let's zero that out. Wait for the snowflake. And let's see how much sucrose is in here. 9.11. I had 9.11 grams of sucrose in beaker 11. So I'm just going to multiply that by 51.4%, and in decimal form that's just dividing by divide that number by 100 to get the decimal form, or you can hit your percent key on your calculator. And so my answer is 4.68 grams. And if that fell within 2% error, then that would have gotten me 4 points. On to task 2, I'm asked to count how many atoms are in my sample of magnesium. Now you could have had iron, copper, tin, or a couple other options I think I had out, but I'm going to, in any kind of dimensional analysis problem, I've always shown you to start with the given, or what you know. I gave you a block of magnesium. Now in a test you would expect some kind of number to appear on your paper, but this is the part you had to do. Here's magnesium 29. 0 the scale. .547. So I just masked that to be 5.47 grams. So that's the number I'm going to start with, and I'm going to turn that into number of atoms. Well, I don't have a conversion factor that goes directly from grams to number of atoms, but all three of my conversion factors do connect to the mole. So I'm going to turn grams into moles. My conversion factor for that is called the molar mass. That's the number on the periodic table if you have a mole of it. So for my periodic table, I can see 1 mole of magnesium has a mass of 24.30 grams. Now, whatever my calculator computes here at this stage is going to be in terms of moles. I'm not there yet. I need to get atoms. So I can use Avogadro's number, or the conversion factor. 1 mole of anything is 6.022 times 10 to the 23rd of whatever I'm counting, in this case is atoms. I cancel out the moles and punch these in my calculator. So here I go, 5.47 divided by numbers on the denominators, 24.3 times 6.022 times 10 to the 23rd, and 1.36 times 10 to the 23rd. 1.36 times 10 to the 23rd atoms is what was in my sample of magnesium. And if that was within 2% error, then I got myself 4 points. On to task 3, I'm asked to turn in 1.07 times 10 to the 23rd aluminum atoms to my teacher. So the only thing in the lab that I have to measure was a scale. So I need to turn amount of atoms into grams. So I'm going to start with the number I'm given here is 1.07 times 10 to the 23rd atoms. Again, I don't have a direct conversion factor between atoms and grams, so I'm going to take that to the moles because all three of my conversion factors are connected to the mole. So 6.022 times 10 to the 23rd atoms, molecules, apples, oranges, or anything that I'm counting is in 1 mole of whatever I'm counting, in this case aluminum. Alright, so now that I have moles, that's no problem. I can turn that into grams using the molar mass, using my periodic table. So 1 mole of aluminum has a mass of 26.98 grams. 1.07 times 10 to the 23rd divided by Avogadro's number. Since they both had 10 to the 23rd, I didn't even need a scientific calculator. I could have just punched in the coefficient. 1.07 divided by 6.022. All right, so it's 4.79 grams. So we need 4.79 grams of aluminum. All right. So in here, I just dropped a couple gazillion, but in here were, on to task 4, I'm asked to measure out 0.128 moles of calcium chloride, again in the lab. So I need to convert moles into units of grams because that's what I can measure using the equipment I had available to me. So moles to grams, that's just your molar mass is going to be your conversion factor. That's from your periodic table. Let's convert 0.128 moles of calcium chloride. Now actually, before we do that, let's get the formula unit for this ionic compound. Calcium forms 2 positive cations and chlorine forms 1 negative anions. We'll crisscross these numbers to get the ratios in the formula unit. So the formula for calcium chloride is CaCl2. So let's actually get the molar mass. We got 40.08 plus there's 2 of these guys. That's going to be 70.90. And then add them up. And then the molar mass for calcium chloride is 110.98 grams per mole. All right, so now that we know that, we can use that as our conversion factor to convert moles to grams. Put moles on the other side of our conversion factor, and the number of grams is 110.98. All right, let's punch those numbers in. And 14.21. Grams of calcium chloride is what I had to measure out, put it into a beaker, a clean, dry beaker, and give that to my teacher. And if that was less than 2% error, I got myself another 4 points. All right, I'm not gonna record myself measuring 14.21 grams of this salt because I think you know how to do that. So here's the station with bottle number 74, and the label right there tells us is 1.89 liters. So that's what we'll work with. That's the volume in the bottle. So we can say, since it's an empty bottle, that's how much air is in the bottle, 1.89 liters. So we'll take 1.89 liters and turn that into number of air particles. So we don't have a conversion factor going directly from volume to number of particles. So we'll take that to moles. So we do have a conversion factor that converts gases, which is air particles or gases. And we're close enough to STP that you didn't have to worry about that. And the conversion factor is in 1 mole of any gas at STP takes up 22.4 liters of volume. At this point, we have our quantity in terms of moles. So we can turn that into number of particles by using Avogadro's number. 1 mole of anything, atoms, molecules, particles, there are 6.022 times 10 to the 23rd of them. In this case, air particles. (1.89) divided by 22.4 times 6.022 times 10 to the 23rd. So there's 5.08 times 10 to the 22 particles of air in that bottle. Finally, task 6, I'm asked to put 1.57 times 10 to the 24 molecules of water into a beaker or a container. So again, the only thing I have available to me is a scale. So I want to convert molecules into grams. so I can measure that out on my scale. I'm gonna get the molar mass here. I know I'm gonna need that, so I'm gonna do that first. For H2O, which is water, I have 2 hydrogen, so that's gonna give me a mass of 2.016, and I'm gonna add that to 1 oxygen, which is 16, and so the molar mass of water is 18.01 or 18.02 grams per mole. I'm going to use that as my conversion factor if I need to go between moles and grams, which I will have to do. All right, 1.57 times 10 to the 24 molecules of water is what I'm asked to measure out. So we're going to turn that into moles. That'll get me to moles, and once I have moles, I can take it over. Once I have moles, I can take this over to grams by using the molar mass of water. .57 times 10 to the 24 divided by Avogadro's number times 18.02. 46.98. grams of water is what I need to put in to a container, give it to my teacher. All right, if I'm under 2% error, got myself another 4 points. So our final task is to count 1.57 times 10 to the 24th water molecules, and that equates to 46.97 grams of water. So I zeroed it out.
That would work. Yeah? Yeah. Just one pass. Like, don't do it like multiple times. Just like, pass. Okay. I'll try.
And that'll be close enough.
I'll do it once with
46.97 is what we're looking for.
I have trust. I have much trust in you.
Ooh.
If you mess up, like, it's my fault.
Good.
So.